Yes, moving charges and magnetism. The questions based on force on moving charge in electric field and magnetic field and Ampere's law, right? Right, guys. Yes, guys. One small concept based on question number 1 and 2 in level 1, exercise 1 and level 1, exercise 2. Open your books. Level 1, exercise 1 and exercise 2. Exercise 2, first question. Exercise 1, first question. These questions are based on a small concept. Let me read the question first. Then we will go ahead with that small concept. Then we can work out that. The question is: yes, the north pole of strength pi ampere meter is moved along or moved around a circle of radius 10 centimeter which lies around a long straight conductor carrying current of 10 ampere. The work done is nearly. In exercise 2, it is given that right. First question: the north pole of strength pi ampere meter is moved around a circle of radius 10 centimeter which lies around a long straight conductor carrying a current of 10 ampere. The work done in moving it by 2 revolutions is To understand that, let us see briefly a small concept. See here, if we have, we can write down the heading. The work done in revolving the north pole around the current carrying conductor. Work done in revolving. Yes, not of this. The work done in revolving and north pole, or you can say a pole of strength, means pole strength M. There is a pole strength M around a current carrying conductor around a current carrying wire or conductor. Yes. How to find the work done in revolving this a north pole, or you can say magnetic north pole actually it is, of some pole strength M around a conductor n number of times around a current carrying conductor n times around a current carrying conductor n times. To understand this, let us consider this is a current carrying wire in this current I is flowing. Is it clear, everyone? So now around this we are trying to move or revolve. Yes, ma'am. We are trying to move or revolve a unit north pole of pole strength M. What is M here? Pole strength of a unit, not unit north pole. Unit means pole strength of unity. So north pole of pole strength M, right? Let us say we are moving this in this direction. Okay. Now let us consider the work done in moving this pole to a small distance, pole of pole strength M, to a small distance dl along this loop, provided the distance of this point or the radius of this loop is small r. then you can say the small amount of work done in moving this is usually work done is equal to what? Force into displacement. So you can write it as force F vector dot displacement vector. Okay? Small work done is equal to this. But here, what is the force? We are moving this north pole, just this side current carrying conductor. Here, this current carrying conductor is producing some field. In that field, we are moving it. The field produced by current carrying conductor, the magnetic field be present here. Okay? In this field, we are rotating this, or revolving this. So you can take this as force, magnetic force into dl vector, not dl vector. But by definition, if you observe the electric field and electric force relation, we know electric field is equal to force per unit charge. Similarly, magnetic field can be defined as magnetic force per unit north pole vector, we call it as. So from this you can say magnetic force is equal to m into b. So this further you can write as m into b vector dot dl vector gives you small amount of work done in moving this through a small distance dl in the electric field b. Right? Now total work done in revolving it is given by W is equal to what? W is equal to integral of dW. Right? It is equal to integral of m into b vector dot dl vector. You are following? m into b vector dot dl vector. M is a constant for a given pole. You can take this out and you can write it as m into integral of b vector dot dl vector. Let's say this is 1. But from Ampere's circuital law, we know that integral of b dot dl is equal to what? Mu into I enclosed. So this if you replace here, the entire integral of b dot dl as mu naught I, you will get the work done is W is equal to m into mu naught I is the total work done in moving a north pole of pole's length m through along circular path for one turn. This is the work done. This is for one turn. Whereas if you want to rotate this for n number of turns, for n number of turns, you can write this work done is equal to mu naught into I into pole's length into n, or you can write it as n mu naught I is the total work done. Is it clear? This is small and very important concept. In application you can call it as what you call Ampere's law. You have to keep in mind. Okay? Now all the data, all the parameters are given in the question. You can just directly substitute the values. To move this throughout the around the conductor once. Number of turns is 1. Constant is given 5 ampere meter. Right? What is the constant? 5 ampere meter is given, and radius is given as of circle. Radius is given as 10 centimeters. Anyway, we don't need here radius, right? And current is given as 10 ampere. So m is given, n is given, I is given. Mu naught is what? Mu naught is equal to what is mu naught? Permeability of free space. It is equal to mu naught is equal to what? 4 pi in 10 to the power minus 7 units. What is the unit? Units. What is unit of mu naught? From Bio-Savart law we have to understand that. Okay? Right. Next. So this question number 2 is based on electric force. But question number 2 is based on electric force. Electric force. The work done only I asked to find. Level 1, exercise 1, I think In AT material, the question is different. The neat material, the question is different. So you have to cross it. In the neat material, it is given as a charge is locating at the center of a loop, circular loop, and another charge is revolving around that. So what is the work done? To revolve the charge once around the charge which is locating at the center, depending on the different magnitudes. Okay? There, in case of electric charges, the force is, work done is force into displacement. For revolving once, displacement will be 0. I will take it 0. So there you have to be a little careful, so the work done will become 0 in that case. Next, another question in level 1, exercise 1 only. What is that question? Question number 42. What is the question number? Level 1, exercise 1. Level 2, exercise 1. Level 2, exercise 1, question number 33. Right. 33. How many have did this, completed this? 33. We are discussing, I have given some hint in the class. Have you tried or not? 33. No. Right, look. See here. And where is this? This side. Right. Level 2 exercise 1. Level 2. Level 2 exercise 1. Question number 33. The question is, let me read the question. Follow the question first. The question is, two electrons move parallel to each other with equal speed v, then the ratio of magnetic and electric force between them is. Simple question. You have to understand the concept behind it properly. That's it. Yes. The question is, I am repeating the question again. Two electrons move parallel to each other with equal speed v. The ratio of magnetic and electric force between them is. Two charges are there, Q1 and another charge Q2. Right? Two particles having same charge. So Q1 is equal to Q, Q2 is equal to Q. Sorry, two electrons, right? Two electrons it is given. So charge of electrons, two electrons. Electron charge is E, magnitude is considered E, magnitude. Two electrons move parallel to each other with equal speed. Parallel to each other, same direction, with the same speed. Then the ratio of magnetic force to electric force is equal to what? Here we have to first write the expression for electric force acting between the particles and magnetic force acting between the particles. So when two charges are at static condition or in dynamic condition, the force between them is given by Coulomb's law. Yes? So this already we have discussed. Electric force between static charges and dynamic charges is K Q1 Q2 by R square. Let us consider the distance between them is R. Right? Yes? Okay. Where Q and Q2 are A and E. So I can write this as is equal to K is 1 by 4 pi epsilon naught into E square by R square. Let's say this is 1. And what is the magnetic force acting between them? Magnetic force. M is equal to Fm is equal to what? Between the two particles, the charged particles. So if we have external magnetic field, in external magnetic field, if a charged particle Q is moving, then the force is Q into V into B, where V is external field. In that field, if a charged particle of charge Q is moving with this velocity, but here there is no external field, two particles are moving. In this scenario, you have to consider first one particle, it is moving. This charged particle, moving charge, is treated as a moving charge, produces magnetic field. Moving charge produces magnetic field. It can be treated as a current carrying conductor, right? So it produces magnetic field, and that field producing by this charge in its surroundings, another charge is moving. So what is that field produced? We have to find first. Magnetic field produced is given by, according to Biot-Savart law, we can say mu naught by 4 pi into IDL sin theta by R square. So magnetic field here, due to that charge in motion, is nothing but mu naught by 4 pi into IDL sin theta by R square. But what is right? Current. Charge is given. Then how you are considering current here? Current is nothing but rate of flow of charge. Yes. Rate of flow of charge. So small amount of field, if you consider it to small length part of this motion of current carrying charge, you can write I is equal to dq by dt. Can you take I is equal to dq by dt? Yes. So this, if you substitute here, you can get, because of this, you can write it as mu naught by 4 pi into I is dq by dt into dl by r square. But dl by dt is nothing but distance by time. Change in distance by change in time as charge is moving. So because the charge is moving, it is giving the current. It is traveling a distance of dl in every dt time. So that gives velocity. You can write it as dl by dt. dl by dt is v. Then you can write it as mu naught by 4 pi into dq into v by r square. Is this step clear? This is the small amount of field produced by what? The charge which is flowing in unit time. Right? Whereas the total field, if you want, d is equal to integral of this. Integral of this means a small charge we are considering dq part. Out of this, you say you can take as integral of dq will be the total one, or you can write it as mu naught by 4 pi into q into what? What is this? V by r square is the total field. So let us say this is equation 2, this is 3. Let us substitute 3 in 2. Then you will get the magnetic force. Are you following? Then you will get the magnetic force. So you can write magnetic force Fm is equal to QVB. Q is what? Charge of electron. This is E into V into B is what? mu naught by 4 pi into EV by R square. Now we can write it as mu naught by 4 pi, constant out first, and E into E is E square. E square V by R square. That is, this is equation 4. Equation now from equation 1 and 4, we want Fm by Fe. So Fm by Fe is equal to, Fm is mu naught by 4 pi into E square V by R square. Is it E square V? This is only here. Or this V square. V square. V into V. So E square V square by R square divided by Fe. What is Fe? 1 by 4 pi epsilon naught into E square here. E square by R square. R square goes here. So here E square, R square, 4 pi cancel. Anything else gets cancelled? Then what do we get? Is equal to mu naught V square epsilon naught. Or you can write mu naught epsilon naught V square. Denominator, nothing is there. This is the ratio. Got it? This is Fm by Fe. If this is not there in the options, I have to look into the options, I have to verify. If it is not there in the options, we have to accordingly simplify further. Here if you see in the options it is given in terms of speed of light. So here you have to remember one more point that you should know, because C is equal to 1 by square root of mu naught epsilon naught, or square root of mu naught epsilon naught is nothing but 1 by C. If you square on both sides, you get mu naught epsilon naught is equal to 1 by C square. Substitute this here, you get is equal to V square by C square. Right? C is speed of light. So where you should remember that mu naught epsilon naught is equal to 1 by C square, then C is speed of light. You can call it as electromagnetic wave, speed of electromagnetic wave. Speed of electromagnetic wave. Got it? Yes. Next. Question number? Which one? I'm up. I'm up. Oh, okay, let us spend 2 more minutes. Base colors. Nothing will happen. 2 minutes. Any other questions? This side. Yes? This side. Okay. Level 1 exercise. Right. Exercise 1 only. One more question. Actually, I have given a hint, but there that hint I thought is not that much clear, so I would like to repeat that once again. Question number 42. Question number 42. So have you copied this, everyone? Have you copied this? Level 1 exercise, level 2 exercise. Level 2 exercise 1. Level 2 exercise 1, question number 42. The question is, let me read the question once. Can you switch on the fans for a minute? I'm wearing sweater. I may feel more hot. Still, I want fans to be switched on. 2 minutes. 2 minutes. Right. Good. This is what we want. Question number 42. Quickly. A beam of charged particle having kinetic energy 10 power 3 electron volt contains masses 8 into 10 power minus 27 kg or 1.6 into 10 power minus 26 kg emerge from one end of an accelerated tube. There is a plate at a distance of 10 power minus 2 meter, means 10 power minus 2 meter is 1 centimeter, right? At a distance of 1 centimeter from the end of the tube and placed perpendicular to the beam. Beam is moving like this. The plate is placed perpendicular to this. The magnitude of the smallest magnetic field which can prevent the beam from striking the plate. Magnitude of smallest magnetic field which can, I want pin drops, which can prevent the beam from striking the plate is. You have to understand that. Let me give a small diagram. Right. See, let us say there is a magnetic field. So beam of charged particle having a kinetic energy of 10 power 3 electron volts contains masses 8 into 10 power minus 27 and 1.6 into 10 power minus 27 kg. They emerge from a tube. That means they are actually emerging from a tube and entering here. Okay? And they are entering So the plate is arranged at a distance of 1 centimeter somewhere here, so that we are asked to find the magnitude of the smallest magnetic field which can prevent the beam from striking the plate. They are coming here. If you apply a magnetic field here, you can prevent this particle to strike the plate. In what direction you can apply the magnetic field? If a parallel direction or anti-parallel direction if you apply, they with no force acts. So if they move just as it is, then go and they strike. So to prevent that, you have to bend the particles. To bend, you have to arrange the magnetic field in a perpendicular direction. You have to arrange in perpendicular direction. If the field is perpendicular, then the charged particle will deviate because the force will be perpendicular to both the velocity and the magnetic field. So the beam may deviate like this. If the field is more than enough, then it may deviate completely before touching the plate. If it is less, it may go and touch without deviating. So you have to apply strong enough field so that it will bend. So that you can say the radius has to be equal to here mv by qb, or in terms of energy is given. In terms of kinetic energy, 2m ke by qb. If here the radius is directly proportional to mass and inversely proportional to field. Two particles are given, one smaller particle and a larger particle in the beam. So if smaller field is there, it can bend smaller charged particle also. But for larger particle, the field should be large enough, right? So that field you have to consider. That means the field to deviate larger mass, if you consider, that can easily deviate the smaller mass. If the field is bending the larger mass, means it can easily bend the smaller mass. The field which is bending the smaller mass may not bend the heavier mass. The logic is clear? So we have to apply. You have to consider here the larger mass. Out of two masses, you have to consider larger mass, and for that the field you have to calculate. Is it clear? Right? So it is mentioned that radius will be this much only. What is that? This will be the distance. From this is the tube actually. This distance will be the radius you have to consider. That is 1 centimeter. 10 power minus 2 meter will be the radius. So radius is given. So the heavier mass you have to consider. Kinetic energy is same. The charge of that particle. The heavier mass particles charge you have to consider. And for that corresponding magnetic field you have to calculate. Okay, use that and write down B is equal to square root of 2 into m, mass of larger particle, into kinetic energy by charge of larger particle, heavier particle, into radius. That is, the radius here is nothing but 1 into 10 to the power minus 2 meters. Substitute this, you will get 1.414 Tesla. You get 1.414 Tesla. Right? Okay. So these are the remaining numericals. I hope all other numericals are clear for you. So revise these numericals and revise, recapitulate and come.